This is a stoichiometry problem. However, we're asked to balance the chemical equation to start with. So if we look at our initial hydrocarbon, we'd see the hydrogens would go to water. 6 hydrogens would produce 3 waters. However, we're going to need an even number of water molecules so that oxygens are going to end up balancing because they come in 2s in the reagent side. So I'm going to start this balancing by having 2 benzene molecules. That gives us 12 carbons, and the only place the carbon can go is to the CO2 molecule, so that coefficient has to be 12. We have 2 times 6, 12 hydrogens, so we're going to need 6 waters. Now in total we need 6 oxygens for water. We need 24 oxygens for the CO2, so we're going to need 30 oxygen atoms, so we will need 15 oxygen molecules. Now, since we're asked to relate a lot of the different things to each other, I'm going to create a BCA table. Alright, so in this problem, our limiting reagent is going to be benzene. Well, oxygen is in excess, so we're going to lose all of our benzene to go to 0. So if we lose our 0.86 moles of benzene, we're going to gain that much of, or we're going to also lose that much of oxygen, multiplied by some mole ratio. Now we get the mole ratio from the coefficients. The numerator is going to be the coefficient from the compound that we're interested in, and the denominator comes from the limiting reagent. For CO2 and water, we're gaining that amount times some mole ratio. The mole ratio for CO2, 12, is the coefficient associated with the chemical we're interested in, and again, our limiting reagent has a coefficient of 2. For water, numerator is 6 from this coefficient, and the numerator from our limiting reagent, again, is 2. So to find the amount after the reaction occurs, we add before plus the change. Okay, and here we are with our final answers. We have none of our limiting reagent left. We've lost 6.45 moles of water and produced 5.16 moles of CO2, 2.58 moles of water.